Welcome to all of you. I'm so pleased that you're able to join us this evening on our talk, which is designed to complement a lot of the conversations that are going on at COP26 in Glasgow over the next couple of weeks. And I'm sure, like myself, you've been following events closely in terms of some of the statements that are coming out, some of the promises that are being made, and lots of discussion about whether the required action that we need to take is going to actually come from those talks that are going on at the moment. Of course, it's absolutely essential that they do. Those talks in Glasgow are really focused on the urgent need for action. And certainly my colleagues from the wildlife trusts who are up in Glasgow are very much there talking about the need for action to keep us below that 1.5 degrees C, but also recognizing that it's not only about keeping us below that 1.5 degrees sea level, but also adapting to the inevitable impacts that we are already going to experience from climate change. Here in Surrey, we know that we are already experiencing those impacts. Some of you may be aware that last year we had serious wildfires on 2 of our national nature reserves. These are highly protected lowland heathland landscapes. In Surrey, we look after some of the most precious lowland heathland and some of the scarce resource globally. And to see these wildfires coming in and causing the damage that they do can be quite devastating. The one on Chobham Common last year was so serious that the fire service were present for over a week. Conversely, we also are experiencing increased flooding events, and many of you even experiencing the high levels of rainfall in short periods of time will have been caught out with the surface water flooding that generates. And so we know that these impacts are already being experienced. We also know that the impact of climate on biodiversity is significant. So not only is our biodiversity struggling with many of the other challenges that it faces, fragmentation, the fact that we are trying to squeeze so many uses out of our land, which means that there's very little space left for our biodiversity. In Surrey, as in much of the UK, we know that we've lost or are losing over 1/3 of our species. So climate impacts on biodiversity are significant. But the really good thing is, we know that if we repair our ecosystems, if we repair our biodiversity, that will actually help us to both mitigate the impacts of climate change and also adapt to them. Because nature is a fantastic store for carbon. So creating those lowland heathlands, creating hedgerows, looking after our chalk grasslands, all of those things will help us to actually store carbon. But we can also use activities, for example, such as planting hedgerows or woodlands, to help us create natural flood management so that we alleviate those floods that we experience as well. So biodiversity and climate are inextricably linked. And if we look after both through delivering what we describe as nature-based solutions, we actually can create a win-win situation. Because not only do we address the impacts of climate, but we also increase the amount of biodiversity that we have. Even more than that, we also create the opportunity for jobs and for people, young people in particular, to come into this fantastic career that I've certainly been privileged to enjoy for longer than I care to mention now, where you can look after our natural environment. And we're increasingly doing that, not only on the land that we manage as Surrey Wildlife Trust, but also increasingly working with other landowners, because a really important part of COP26 and indeed COP15, which will be looking at biodiversity next spring, is that we cannot do this on our own. We have to do this as a collaborative effort and make sure that we come up with these solutions together. I am absolutely delighted now to introduce my colleague, Ben Siggery, who is going to share with us some amazing insights into the story of paleoclimatology. And it's really important that we understand why we have got to the point that we've got to, if we're going to create the most effective solutions. So I'm very much looking forward to hearing what Ben's going to talk to us about, and I'd like to hand over to him now. Thank you, Ben.
Well, thank you very much, Sarah Jane. So I will just start by sorting out my screen sharing, as we almost do at the beginning of these talks. So hopefully that's in the right place now. Sophie's nodding, good, perfect. So hello everyone, my name is Ben, as Sarah Jane mentioned, and I work at Surrey Wildlife Trust with her and Sophie. I've worked for the Wildlife Trust for about 5 years now, and my job these days is working with the kind of research and monitoring team on the kind of science side of things. And my background is geography at university. I studied quite extensively in terms of environmental change and paleoclimatology, which is why I'm talking to you about it today. So it's not something I get to do in my day job very much, but it's something I really was passionate about at university, and my undergraduate dissertation was very much linked to it. So like I say, not my day job, but something I'm super interested in. So hopefully some of that passion will rub off on you tonight as we delve into the story of the history of our climate. So we'll start off with some definitions, because paleoclimatology isn't really an everyday word. It's not always a word that people have heard of before. And if you break it down into paleo and climate, it makes a little bit more sense. So paleo is a word that means ancient, and we hear it in paleontology, the study of dinosaurs and other prehistoric animals. We hear it in paleoanthropology, the study of early man. And we hear it in things like paleoecology, the study of ancient ecosystems and past environments. And obviously climate is climate. So paleoclimatology is the study of past climates. And more specifically, it's the study of climates for which there aren't any direct measurements. So when I said direct measurement, I mean that something that we can record with a scientific instrument like a thermometer. So obviously now we can do that, and we can take direct measurements of the climate, but it's really only since about 1850, when those things were invented, that we have these direct measurements. So prior to 1850, we have to use indirect measurements to look at our paleoclimate, and we do that through things called proxies. So these things are often biological, but they can be chemical as well, and essentially they're substitutes for these direct measurements. And we're going to go throughout this talk some of those different proxies and how they get used. But obviously that gives us the what, but then we also need the when. So we combine those proxies with dating techniques like carbon-14 is one lots of people have heard about. And we're able to then make assumptions about what was going on in the past, when it was happening, and give us some estimations of what the climate was doing at that time. All of this is based around a principle called uniformitarianism, which is essentially the key words in the name of the talk. The past is the key to the present. And it's about understanding that the natural processes that were active on the Earth 100 million years ago, 1 billion years ago, 5 billion years ago, well, not quite that far, it's not quite that old, are exactly the same natural processes that are happening today and will be happening in 1 million years' time, in 1 billion years' time. Those core fundamental parts of physics, biology, and chemistry work the same way now as they did then. And because of that, we can assume that the organisms respond in the same way then as they do now. So therefore, we can look at what this species was doing 100 million years ago and assume that we can use our knowledge of that species and similar species today to make these assumptions about the past. So for example, we may look at an animal that likes hot climates today. We'll see a close relative of that animal 100 million years ago. So we can assume that that animal lived in a time or place that was quite hot as well, for example, it's very crudely. But the point of doing all this paleoclimate stuff is to understand what has happened to the Earth's climate throughout history and how it has behaved, and show us what's natural, so that we can look at today and say, well, is this now outside of natural, or is it a continuation of trends that we've seen in the past? So we're going to go through that journey, hopefully, in this talk. So like I said, we're going to start with how do we find out about all these past climates. We'll talk about some of the proxies that we'll use and where we actually find this information. So a lot of the paleoclimate record is found from taking sediment cores and ice cores. So basically you get a big cylinder, big tube, drill it down into the ground, and then when you pull it up, you have a core of either sediment or ice, depending where you do it. So sediment cores are often from marine sediments, so they're taken from the bottom of the ocean, whereas ice cores are taken at the North and South Pole. And the point of doing this is based around another principle called superposition. So superposition is essentially saying the stuff at the top is newer and the stuff at the bottom is older. So if you think about at the bottom of the ocean, as sediment gets deposited, the newer, fresher sediments will go on top of the older sediments. So then it's forming this kind of column going upwards towards the present. And the same thing is happening at the North Poles, where you have more snow and more ice being deposited through precipitation. And obviously then the newer, fresher snow is hardening and forming on top of the older snow beneath it. So we can take these cores from either the bottom of the ocean, the North Pole and the South Pole, and we can date them. And we can look at how far the record in them goes back. The great thing, particularly about the ones at the North Pole and the South Pole, is that we can see annual layers throughout them. So we don't even need to bother with things like carbon dating, because you can literally count back through the years looking at the layers of annual precipitation at the North Pole and the South Pole. So we can date them, and we can drill down really, really far into these ice sheets. The longest core from the South Pole is 3 kilometers long. And that goes back covering about 800,000 years of history. The marine cores are not quite as long or quite as old, because at the bottom of the oceans, we're constantly losing and creating new crust as part of tectonic processes, whereas our ice sheets at the North and South Pole have been there for quite a long time. And we'll talk a little bit more about that later, actually. So both of them give us these long-term invaluable records of past climate. And now we're going to talk about exactly what in them are we looking at. So we're going to start talking about those cores as non-biological indicators, and we'll move on to the biological ones in a minute. So starting with the ice cores, like I say, you drill down and you get these really long, very nice annual records of the climate over the last 800,000 years. And you can find out a variety of things from them. So if you're really lucky, you'll get air bubbles, which literally have ancient atmosphere contained within them. So you can take direct measurements of how much carbon dioxide was in the atmosphere at that point in time. So if you're really lucky, you get air bubbles. You can also find dust in them, which is evidence for cooler and drier periods of time. You can look at the depth of those annual layers and see in a wetter year, obviously it will be a thicker layer. And you can also look at the makeup of the H2O, the actual water that's frozen in that ice. So obviously H2O has oxygen in it, and oxygen comes in 2 isotopes that we care about for climate reconstruction, at least, which is oxygen 18 and oxygen 16. And the ratio between those fluctuates through time and is very dependent on temperature. So I won't bother explain the relationship because it's quite complicated, but when you then look at the oxygen making up the H2O in the ice core, you can see what's the ratio oxygen 18 to 16, and from that you can actually create a very precise estimate of the temperature at that point in time. So the ice cores are really, really good, and we've used them to create these long-term records. Obviously, with ice cores, they are kind of spatially limited. They're obviously at the North Pole and the South Pole and not really anywhere in between. But we can be quite confident in the information they're telling us, because the record that we have at the North Pole is almost identical to the one that we're getting at the South Pole. So literally on 2 polar opposite ends of the planet, we're getting the same information about climate. So they're the fundamental kind of component of many paleoclimate reconstructions, because they're very long-term records, they're very detailed in terms of their annual resolution, and they tell us a lot of information, especially about global temperatures. Another example of a non-biological indicator are things called speleothems, which is essentially a fancy word for stalactites and stalagmites. These are kind of mineral precipitation in caves. So again, a bit more elsewhere around the world than the polar ice cap ones. So they give us a record elsewhere, but it's not quite as a long-term record as the polar ones. They can usually go a few 100,000 years, but definitely not the extent of the Antarctic ice cores. The mineral that precipitates is often calcium carbonate, which contains obviously oxygen to tell us again about temperature based on isotope ratios, and also carbon, which tells us quite a lot about vegetation. So obviously the amount of carbon in the atmosphere, at least historically, has been very related to the amount of vegetation photosynthesizing on the planet at that time as well. So we can get quite a lot of useful information from speleothems as well. So biological indicators, and I'm certainly biased because these are the ones I find much more interesting, but not to diminish the importance of the others. They're extremely extensive as a group, and I've listed tons of ones on this slide. We're not going to have time to talk about most of these today, and there are even more beyond this. And it's really a very interesting field of science, based around the idea that if you understand the preferences on the ecology of the species you're finding, then you can assume what the conditions were like at that point in time. Like I was saying earlier, you find something that likes wet, hot conditions, you can assume the conditions were wet and hot. And this kind of thinking and logic in science has been around really since ancient Greece. We have evidence that people like Herodotus were finding marine fossils inland and then deducing that those areas might have been from historic oceans. A really great example of that is actually the Himalayas. There's marine fossils on the peaks of the Himalayas. And you're like, okay, well, how did fish get up there? And it's because millions of years ago, the top of the Himalayas were at the bottom of an ocean called the Sea of Tethys that was south of where India is today. So it really has provided some interesting insights in terms of even tectonic plates and things like that. These kind of fossils were how people like Alfred Wegener even came up with the theory of tectonics. So biological indicators, very important in paleoclimatology and also pretty cool as well. So we're going to go through some of the major ones now. So first up is pollen. Pollen is really one of the kind of star players of biological indicators, and to the extent where it has its own branch of science, palynology, named after it. And it's been for a long time the main technique of long-term vegetation reconstruction. And as you can imagine, pollen is very good at reconstructing vegetation because it's made by plants directly. It has a very direct link to the presence of different species of plants. So like I say, it's been used in huge amounts of work over the last 30 years and has been really fundamental in proving a lot of changes in vegetation across Europe and the Americas and other parts of the world. And it's given us this great insight into long-term patterns and processes, even those which are related to human activity, because things like agriculture, things like invasive species and human-caused wildfires can all be associated to different pollens as well. So obviously, agricultural pollens are related to the increase in agriculture, and we can see those increasing in the fossil record. So the reason why these are great indicators, there's a couple of reasons. First of all, the walls of pollen are made of something called sporopollenin, which is a great word, but it's a material that's very resistant to degradation. So when pollen is deposited in mud, and then that mud gets buried and eventually becomes sedimentary rock and things like that, the pollen preserves pretty well. You know, for a tiny, tiny thing, it's very well preserved and creates very good, solid fossils from it. It's obviously produced in huge quantities as well, in the order of billions. You know, plants just spew this stuff out constantly. So there's absolutely tons of it. It's very abundant in the sediment. And the other great thing about it is that the shape is very often related to the function of the pollen. So wind dispersed pollen, they all look a certain way. And those shapes, because they're so specific and functional, are very easily linked to a specific species. So they're easy to identify, there's tons of them, and they preserve very, very well. So all in all, a really good candidate for a successful biological indicator. However, there's a couple of issues with them in the sense that because they produce so much pollen, and because not all plants produce pollen, there can be kind of mistakes that have been made in the past, or misrepresentations by pollen just being dispersed really far away from the source. You know, if there's absolutely tons of pollen and it blows very far away to an area where that plant doesn't actually live, what kind of assumptions might we end up making in error because of that? So to kind of complement that, there are other indicators that we can use. So macrofossils are very commonly used in combination with pollen to improve the picture that pollen has given us about an area, pretty much. So a macrofossil is something that is big enough to see with the naked eye, but small enough that you really still need a microscope to look at it properly and identify it. So often things like plant seeds, oospores from aquatic plants like chorophytes, bits of insects. So all kinds of weird and wonderful things get counted as macrofossils. And they're very complementary to the pollen in the sense that they're the opposite. They're produced in small numbers, but they're produced very locally. So pollen is produced in large numbers and it gets everywhere. So if there's pollen in a place, but there aren't macrofossils, then it raises a question about whether that plant actually lived there. But we've seen that actually macrofossils have been used to correct these pollen studies, and they've been used to say, in some cases, yes, there was that plant there because we've also found macrofossil evidence. So like I was saying, the limitations of pollen are really countered by the use of macrofossils, because you will get macrofossils for plants that don't produce pollen. So for example, aquatic plants, many of them don't produce pollen. So macrofossils are a really good one for those. They can be indicative of animal remains as well as plant remains. And they have this really highly localized even representation, because something larger and with more weight to it isn't going to blow tens of kilometers from the point of origin. So it really kind of brings home a point that it's not a competition between different biological indicators, and the best studies are multi-proxy studies, because they use the strengths of the different indicators to work against the weaknesses of the others. So all of them have got pros and cons, but the best possible outcome you can get from your reconstruction is by using all of the tools available to you and looking at the combined picture of all of them. So I think the kind of synergy between macrofossils and pollen is a nice way to illustrate that. So next up on our list are things called diatoms. Diatoms are an enormously successful group of microscopic algae. There's, we think, about 2 million species of them. There's probably loads more that we've just never discovered. And they are probably more than pollen used in paleoclimate studies beyond other groups, because they're great for a huge variety of reasons. They have been around since the Jurassic, so they're a pretty long-term record, and there's a real global distribution of them. Anywhere there is water, there are diatoms pretty much. So there's tons of species of them. They're all around the globe, and they've been around for at least sort of a good 200 million years. The other really interesting thing about them is that they have silica in their cell walls, which is very weird for an organic thing, because silica is basically glass. So when these things die and they are preserved in sediments, they leave these very delicate glass fossils behind. And that's what you can see in the imagery there. They're very small, but they are incredibly detailed and complex in that kind of glass print that's left behind of them. And again, like the pollen, they have very distinctive structures, and you can see the variety of them in that, even within that picture. So we can quite easily say the different species that's associated with those different remains. Because there are so many diatoms, they are incredibly specific in their preferences and requirements. You know, they have very small ecological niches. They don't, you know, so they're quite fussy about where they live. And that also makes them a great indicator of past climate conditions, because they're very sensitive to any changes. So looking at the entirety of a population of diatoms gives us a very detailed picture of what's going on. In particular, they're great for things like water temperature, salinity, light, nutrient availability. They've been used in loads and loads and loads of studies across all kinds of fields within paleoclimatology. So they're one that is very, very commonly used as well. The last big group of things we're going to talk about are the ostracods. So these are a little bit bigger in scale now. Ostracods are small crustaceans, so related to things like crabs and lobsters. They are still crustaceans, but they're about the size of a poppy seed. And if you've ever done something like pond dipping, you probably will have seen them as little dots floating around in your water that you just didn't realize were alive. but they look like these kind of weird baked bean shaped things you can see on the image in this slide. They live their life kind of enclosed in a shell, and then they have feelers that they can poke out as they filter feed through the water. And that's what you can see in that diagram there. They aren't quite as diverse as diatoms. There's probably about 65,000 species that we know about, and maybe a couple more thousand that we haven't really quite identified yet. But what's really unique about them is the longevity of them in the fossil record. They've been around for about 450 million years. So 450 million years extends almost all the way back to the beginning of complex life in the Cambrian explosion, where the fossil record even begins. So the ostracods are a very consistent presence in our record throughout the majority of time that, time that we can at least know about in detail. So they're really useful from that perspective as well. They have calcium-based shells, so like our bones, calcium carbonate as well is in their shells. So again, like our bones, they'll preserve very well in sediments. Lots of them live in the oceans, so naturally when they die, their shells fall to the bottom and they fossilize in the sediments. But like the diatoms, they will live absolutely anywhere there is water. They live in rivers, lakes, ponds, soils. There is even a species of ostracod that lives inside of a frog's rectum, which is a fact I absolutely love, but proof that they will live absolutely anywhere there is water. So as with the diatoms, we look at the ecology of these species and we say, what were their preferences? Okay, that's going to tell us about the conditions that were present at the time that animal was alive. There's a couple of complications with them in the sense that the baked bean shaped shells are not quite as distinctive as the pollen and the diatom remains, so not as easy to identify to species level. They're a little bit more complex as organisms than diatoms, so they have sexual dimorphism, which means the males and the females look different. Sometimes there's valve asymmetry between them, so their shells don't quite match up with each other just because they're a bit weird. And also, as they grow, they molt their shells and move into bigger ones. So there's lots of kind of remains of younger ones that then might be mistaken for a smaller species, and vice versa with the older ones. So there are complications with them, but they have this unique benefit of being so old and so having so much longevity throughout our fossil record. As with the oxygen isotopes in the non-biological indicators, you can look at the oxygen ratios inside the calcium carbonate of their shells to, again, make inferences about past temperatures, past hydrological regimes in additional ways other than the species preferences. So before we move on to kind of the story throughout time, I just wanted to touch on transfer functions, which are a little bit of insight into how these biological indicators actually get used in science to create the reconstructions. So what we've talked about so far is assumptions. So we're saying, okay, this diatom likes these conditions, so therefore it was like this. Whereas using a transfer function, you can translate that assumption into some kind of numerical value, which really gives you kind of the leg up in terms of your reconstruction. So this technique was invented, I think, in the kind of 80s or 90s, and it's been a really kind of core part of paleoclimatology and paleoecology since it was invented. The idea is that you create something called a training set. So you look at the diatoms that live in your lake today, and you see what, for example, pH those diatoms like to live in. And then you'll take that, so then you can work out a way to estimate the pH of the water based on which diatoms are there. You then take that logic and apply it to a lake from 2000 years ago with some diatoms in it. And you can say, oh, okay, the same ones are there, so the pH must be the same. And if different ones are there, you can say, oh, well, the pH must be a bit different. So using that logic, you can estimate what the actual pH value was, or a different chemical parameter, based on the assemblage of animals that are there. This was really instrumental in the kind of late 20th century, when environmentalists were trying to convince the government, essentially, that freshwater acidification was happening. So up in the highlands of Scotland, where the lakes are very sensitive to freshwater acidification, they did some of these transfer functions, and they proved that the diatom community was indicating a massive shift towards more acidic water compared to the kind of 100 years prior, where there were less nitrogen emissions. So this work was used to go and have a go at the government and say, okay, we need to reduce our nitrogen emissions and clean up our act. And as a result of that, freshwater acidification is really kind of on the decline as an environmental problem, whereas it was very, very prominent in the kind of late 90s, early 2000s. So transfer functions are, as I said, a very, very useful tool in our arsenal of paleoclimate reconstructions by giving us that kind of upper edge, by letting us translate an assumption that's a bit more qualitative into numerical quantitative values. So what have we actually found out from all of these different things, all of these different fossils? What have they told us? It's a very long story, as you can imagine, as the history of the Earth. And I will apologize in advance for how long we're going to spend on this slide, because as you can see from the graph, there's a lot of history to kind of sift through. And paleoclimatology as a science has achieved this in really the last 30 years, because, you know, it's only about 30 years old as a science. And it's been able to reconstruct fairly confidently what the temperature has done all the way back to about 540 million years ago. And to some extent, even beyond that. But this graph starts at 540 million years ago. 540 million years ago is when we had an event called the Cambrian explosion. So it's at the beginning of a period called the Cambrian period. And it's where we just have this massive expanse in evolution, and biodiversity just blooms out of nowhere. And we have a real transition away from kind of amoebas and single-celled organisms and a couple of jellyfish into kind of insects and arthropods and weird and wonderful things that live at the bottom of the ocean that are, you know, big enough to leave fossil remains behind. And because of the presence of those things, we can have these kind of reconstructions with a little bit more confidence. So before we start working our way through the graph, I'll just find my laser pointer. Hopefully you can see that. You can see that it's split up into these kind of different colored sections. And it's worth noting the change in scale as we move along. So the orange part of the graph is kind of working in 100 million year increments. The green part is in 10 million year increments. And then it gets sort of finer and finer resolution all the way down to this end where it's only in 5,000 year increments. So it's worth kind of keeping that in mind when we're looking at it, that it's not on the same scale as we move through. Also, this bar at the top, we're going to kind of refer to it throughout, but I'll come back to it a little bit more towards the end of my waffling on this slide. So starting at the beginning of the story, like I said, we've got the Cambrian explosion right up here, and we can see like this rapid warming going into the Cambrian explosion out of nowhere. So it's, you know, hypothesized that potentially all of that warmth and energy maybe enabled some of that rapid evolution. But we can see that the period covered by this orange line, which is the Paleozoic and the Mesozoic. The Mesozoic is the bit with the dinosaurs, and the Paleozoic is the bit before that, pretty much, fluctuates quite dramatically from right at the top of this graph to all the way down at the bottom. And what we actually see with these really dramatic fluctuations is the different mass extinctions that occurred throughout this period. In particular, this one down here, where it zooms all the way right to the bottom of the graph, was the Permian mass extinction. And this is when 96% of life on Earth went extinct. So literally 96% of stuff died. So we, you know, very narrowly escaped life in general dying out there. And that's the biggest mass extinction that's ever happened. And we don't quite know the cause of it. We think it was to do with sort of mass scale catastrophic volcanoes and eruptions and things like that, but that's something for another talk probably. So like I say, we have these really big catastrophic shifts in climate all the way up to the end of the orange line here, which is 65 million years ago, and the end of the dinosaurs. So again, not quite as dramatic as the Permian, but we do see a big kind of move downwards, which is likely a result of the meteorite hit, where lots of ash was put into the atmosphere, similarly to the Permian volcanism. the ash in the atmosphere causes even a lot of cooling globally, and then we see loss of species and things like that. We're going to talk in a little bit more detail about how volcanism can affect climate later on, but it was likely the cause of some of these big mass extinctions throughout this period of time. And then we see, kind of moving away from that and moving into the green section of the graph, the climate is generally quite stable from here onwards. We see kind of a big drop over the kind of 60 million years following the dinosaurs, but then it is generally much more stable, and we don't see quite such dramatic movements in the graph, even with the reduced scale. So moving into the green section of the graph, we're now in a period called the Cenozoic, which is what we're still in today. And we see it kind of reaches a peak here, which was called the Paleocene-Eocene thermal maximum, which scientists think was triggered by what they call an oceanic burp, which is a big release of methane into the atmosphere. So they think it caused this kind of big spike in warming here. But since then, the Earth has been cooling down. And in particular, the cool down has kind of come in line with the transition here from a greenhouse state to an icehouse state. So to cover what this kind of weird green and blue line is talking about, we need to make sure we understand, first of all, that greenhouse and icehouse are not the same as an ice age. They're much, much bigger periods of time and much more dramatic shifts in the Earth's climate. So an icehouse state of the Earth is when there is ice present at the North Pole and South Pole, basically. And a greenhouse state is where there are no ice caps whatsoever. So there's no North Pole, there's no Antarctica, no big polar ice caps at all. So in general, the climate is massively warmer than it would be in an icehouse state. And you can see it back in the orange section of the graph, it flip-flops between those two states. And many of the big dramatic shifts and mass extinctions are associated with the switch from one to another. But going back to the green bit, and the long blue bar here, the icehouse state that we're currently in started about 33 million years ago and is still ongoing today. So that's one to hold on to for later, that we are currently in an icehouse phase of the Earth. And as you'd imagine, icehouse suggests that the Earth is relatively cold at that point in time, or at least it should be. And we can see that's why throughout this kind of green, black and blue line, the temperatures are much more towards the lower half of this graph rather than the upper half like it is over there. So like I said, about 33 million years ago, we transitioned from greenhouse to icehouse. And that's when our ice sheets, as we have today in the North Pole and the South Pole, start to form. And people think it was potentially the result of a variety of different things, like the development of the Himalayas or the opening of the Drake Passage between South America and Antarctica, which affects kind of global circulations of temperature, oceanic circulations of temperature. But yes, since then, we've been in this icehouse state ever since. So as it is such a long story, we don't really have time to talk about the whole thing in loads of detail. So we're going to start about 2.5 million years ago and work our way forward incrementally. So the Quaternary period is the current period we're in within the Cenozoic era. So the Quaternary, like I say, started about 2.5 million years ago. It is a glacial period, so it's when there are ice ages throughout it, and it's really associated with a kind of cyclic growth and shrinking of the ice sheets at the North Pole and the South Pole. So it is an ongoing glaciation because there's lots of ice present throughout it, but it does have these big fluctuations up and down that we'll talk about in the next couple of slides. It's split into two separate epochs, the Pleistocene and the Holocene. The Pleistocene being everything up to about 12,000 years ago, and the Holocene being everything onwards. So the Holocene is what we're in at the moment. In theory, again, something we'll come back to later. So like I say, very much associated with rapid growth and shrinking of ice and lots of glaciation in the Northern Hemisphere in particular over places like Russia and Canada. So what has been causing this kind of cyclical pattern of ice and then less ice? So we see a kind of cycle between things called glacials and interglacials. So glacials and interglacials aren't exactly what you'd think about of an ice age as an ice age. They're much longer kind of periods of time sometimes. So the glacial cycle that we've seen throughout the Quaternary is on about 100,000 years at a time. You have stints of 80 to 90,000 years where you're in a glacial period and everything's really icy. And then you have 10 to 20,000 years in an interglacial where everything's a bit warmer and more pleasant. So you can see on this graph here, the kind of flip-flopping between interglacial, back down to a glacial, interglacial, glacial, et cetera, and very interestingly, you can see where we are at today is in this interglacial bit at the end of the graph here. So the current interglacial we're in started almost 20,000 years ago. I think it's 15 to 20,000 years ago. So you can imagine then that raises questions about this cycle and thinking about, are we actually due to go back into one of these glacial periods? And actually, is that going to happen now with the impacts that humans have had on the climate? And again, something I'll probably try and talk a little bit more about as we go through the talk. So like I say, we've flip-flopped between interglacials and glacials on a fairly consistent cycle. There are kind of blips throughout them, which are called stadials and interstadials. Those are the kind of little ups and downs within the larger glacial periods. But generally, it's these very consistent and predictable periods. And they're caused by something called Milankovitch cycles. So Milankovitch cycles are often known as orbital forcing. Milankovitch is just the name of the guy who came up with them. But what they're talking about is about the position of the Earth in relation to the sun. And as you can imagine, the position of us in relation to the sun dictates quite heavily what our climate is doing. Planets closer to the sun than us are much hotter, and planets further away from the sun than us are much cooler. So it's not quite that extreme, but within our own orbit, we do move around a fair bit. And scientists think that this is very much the reason that is behind these kind of 100,000 year cycles. So you can split up orbital forcing into three categories: precession, obliquity, and eccentricity, more colloquially known as wobble, tilt, and shape. So with the wobble or the precession, that's about how the Earth actually wobbles around its own axis. So you can imagine if you have a spinning top, you spin it, it will go around in circles, but as it loses momentum, not that the Earth is, but as it loses momentum, it will wobble a little bit as it's spinning. And the Earth does exactly the same thing as we rotate around our own axis. So as we wobble about, you can imagine that might cause certain parts of the Earth to be closer to the sun, certain parts of the Earth to be further away from the sun. So the wobble then definitely has an impact on our proximity to the sun. The tilt or the obliquity is about where we are sitting on our own axis. So our own axis kind of fluctuates in around a 3-degree range. So it's a very subtle fluctuation, but sometimes it's slightly more vertical, sometimes it's slightly more diagonal. And again, you can imagine if it's in a more vertical position, the Earth is kind of more equally spaced from the sun. But if it's in a more diagonal position, it might mean that part of the Earth is closer to the sun, whilst the other half is further away from the sun at different times of year. So again, something that can very much influence the climate and cause things like more intense seasons. Lastly, the eccentricity or the shape is about the shape of our orbit around the sun. So we very typically see a kind of ellipsoid orbit or an oval shape that we move around the sun in. But in reality, again, that fluctuates between being more circular and being more ellipsoid. So kind of it squishes and then stretches out again over hundreds of thousands of years. And again, if we're more stretched out, it means that certain points in our orbit will be further away or closer, whereas if it's more squished and more circular, then it's quite even throughout the year. So we have these three factors that all kind of work on their own cycles within the 100,000 year cycle, but the combined forcing of them basically causes those interglacials and glacials we were talking about before. So you can see on this graph here, that's their kind of own rhythms. Then the combined rhythm of them comes together in our stages of glaciation line there. So we have the points that were interglacials are just happen to be at those same points where all three forces work together to create a generally warmer climate. So we see a real clear intrinsic link between the movement of the Earth in its orbit and the fluctuation between these glacial and interglacial periods. And like we were saying before, again, we can see kind of on this graph towards this end actually, that we're in this interglacial stage at the moment, and it's been going on for a while already. So these forces should naturally be pushing us back towards a glacial that many scientists argue we're now kind of overdue. But with our current modeling of predicted climate over the next kind of 10,000 years, we're not seeing ourselves go back towards a glacial stage at all. We're seeing ourselves staying in that interglacial period. So again, we'll come back to it more later, but we're now seeing the beginning of human forcing overpowering this natural orbital forcing that's been causing these 100,000-year cycles for millions of years now, but we've broken it. But again, more on that later. So fast forwarding quite a lot into the Holocene. The Holocene is the current epoch that we're in, with a question mark, as you see there on the slide. And it's the last kind of 11.7 thousand years in the Earth's history. Like I said, it's this current interglacial or warm period that we've been in. And the graph you can see here, we come out of the kind of last ice age that we experienced, and the kind of lowest last glacial maximum was around 16,000 years ago. It's been warming since then, and around 11,000 years ago we hit into our kind of Holocene climate groove, and since then it's been relatively stable throughout here, with a few minor blips up and down. There was a event about 8.2 thousand years ago called the Younger Dryas, which we think was caused by the ice sheets on top of Canada melting, and you saw this kind of big drop in temperature. But apart from weird things like that, it's been pretty stable. And what's really interesting in particular, relating back to human civilization with this graph, is that it very much corresponds with the dawn of civilization and the beginning of agriculture in places like the Fertile Crescent. The stability that the Holocene has provided us with has enabled human civilization to kind of rapidly proliferate and grow the way it has. We have this kind of movement into nice, warm, stable conditions. Agriculture takes off, and from there, human civilization goes from strength to strength. We don't have to deal with many dramatic shifts in climate, and generally everyone does really well. And obviously we get to the point where we're at today because of that stability, arguably. So zooming in even further now to the last 1,000 years. So the last 1,000 years is represented by a graph called the hockey stick, and it's very famous for looking like a hockey stick, but also for really clearly illustrating what is going on in a kind of context that is comparable to our modern climate. Because when you kind of go back through time and we look at these slides with these crazy variations, the Earth was so different back then. The continents were in different places. We had vastly different compositions of gas in our atmosphere. What was going on here is not a comparable point to our modern situation on Earth. So you can't look at this and be like, oh, well, it was warmer then, because it's not a fair comparison. Whereas when we look at our hockey stick graph, what the Earth was doing 1,000 years ago is a fair comparison to today, because the continents were in the same place. Lots of other things were very similar in terms of ice sheets, atmospheric composition. It is a fair comparison. It's what we should be comparing our modern situation to. So going back to this graph, the very important point here is that we see the merging of the instrumental record, so the modern record with our thermometers and stuff, with all of these paleo records. So here, the red line is the instrumental record, all of the thermometers and stuff. And then all of the kind of wibbly wobbly lines over here are the different climatic reconstructions from different proxies and different studies and different working groups and things like that. So you can see with a few kind of blips, the proxies from 20 odd studies pretty much agree with each other. And then as you move towards the beginning of the red line, they continue to agree with the red line moving forwards. So we can be fairly confident then from the kind of overlap window that the proxies are doing a pretty good job of calculating temperature, because here they're very much aligned with the instrumental record that we have a high confidence in. So what we see here really is the dramatic shift towards warmer temperatures in the last kind of 100 years, 150 years of human history, compared to what's been relatively stable throughout the last 1,000 years, and prior to that, relatively stable for the last 10,000 years. And on this graph, because it's so zoomed out, you can't quite see the big hockey stick jump at the end of it, but you can see here where the arrow is pointing to 2004, and you know, that's 15 years ago now. Where is it? Probably up here somewhere now. So we really have we've created as humans this unprecedented shift in our climate that has moved away from natural conditions, because these are the natural conditions, these are the natural conditions, and we're here. So again, probably going to hammer that point home quite a lot throughout the rest of this presentation, but we're moving into an era where science has really unequivocally, big word there, proved that this is happening. And there's another good slide coming up about that. But before we move on to all of that doom and gloom, there's two little blips throughout this 1,000-year window that are quite interesting to look at. One of them is the medieval warm period, which is kind of between 1900 and 1300 AD, sorry, 900 and 1300 AD, and then the Little Ice Age, which is during the kind of Renaissance to Victorian era. So the medieval warm period, like I say, was during the medieval era, and global climate in that era was about 1 degree warmer than present. We have quite a lot of historical evidence that supports that. Lots of that is from Europe, because obviously lots of civilizations in Europe were creating historical records around that time, but other records from other civilizations do suggest that this was a global phenomenon. We have lots of nice anecdotes about grapes being grown in vineyards in England, Greenland being green, wheat being grown in Norway, and the kind of theory that the Vikings, who got to America way before Christopher Columbus, were able to do it in this period because of the ice-free seas around Greenland. They were able to cross right over into kind of Canada and North America and have some small colonies over there. So that was kind of this blip in the graph around here, this warm bit over here. And then we have our Little Ice Age as well, which was, like I say, between the Renaissance and the kind of Victorian era. This one was about 0.6 degrees cooler than present temperatures. And again, what we know from historical records suggests it was a global phenomenon. And again, lots of nice historical anecdotes about the Thames freezing over, Iceland kind of dying because of crop failure, which is not so great. And then things about the Dutch fleet being locked in ice and unable to move. But what I think is really interesting about both of these events is that they show what these small numbers of 1 degree C, 0.6 degrees C actually mean on the ground in reality. Because when we hear about climate change, we're like, oh yeah, 1 degree C, that'll be all right. That's not too much. But actually, small changes in global temperatures have caused quite big differences for day-to-day life. You know, in our current situation, we cannot really grow grapes in England, and Greenland is not really that green. Whereas, you know, we also don't have a regularly freezing over Thames with ice thick enough for them to have festivals out on it. So relatively small fluctuations in global temperatures have quite dramatic on the ground impacts, especially with this kind of recent historical context. So these kind of events are very much worth keeping in mind when we're talking about, in things like COP26, how much climate change are we promising to stop at? Because if 0.6 degrees C can do things like this, what is the 1.8 degrees that they're promising as a minimum going to do? So in terms of short-term climate forcing that is responsible for some of these events like the Little Ice Age and the medieval warm period, we have volcanic eruptions, like I mentioned before, and also sign of variability in the sun's radiation. So volcanism is a really common thing that causes short-term changes in climate, because you have a big dramatic volcanic eruption, lots of ash and debris gets spewed into the stratosphere. While it's up there, the particles of ash act as aerosols, which reflect solar radiation back out into space, means it can't get down to the Earth's surface and warm it, and you have a cooler period of climate as a result. We have modern records of this kind of thing. So in 1991, Pinatubo erupts in the Philippines, and we see a kind of 2 to 3 year cooler period for Southeast Asia and that part of the world. So and then obviously a couple of years down the line, enough rain has fallen that those start to be washed out of the atmosphere and it goes back to normal temperatures. But Pinatubo, obviously a bad eruption, but not on the scale of some of the eruptions that we might be thinking about back in the kind of Permian mass extinction and the Cretaceous mass extinction. Those kind of eruptions would cause a global coating of these particles that would be so high up into the atmosphere that it would take a long time for them to be washed out, rather than a couple of years like we see with Pinatubo here. Within kind of five years, really, the climate's returned to normal. So volcanic eruptions can be big, pivotal things in short-term climate forcing and kind of catastrophic events that come as a result of climate change, but they're short-lived and they're not obviously consistent because they are associated with eruptions, which are not consistent either. The other thing that is responsible for a lot of short-term fluctuations in climate is the radiation given off by the sun. It works on about 11-year cycles where some of the time there's more radiation coming out, some of the time there's less radiation, sometimes there's solar flares, sometimes there's more sunspots, and we just see the kind of fluctuation because of that throughout different windows of time. We think that the medieval maximum here associated with the medieval warm period and the Maunder minimum even associated with the Little Ice Age are so both of those periods are directly as a result of the kind of solar variability. And we see this on our, we do see this on our 11-year cycles. We see it throughout the last 1,000 years in the Holocene, but the effects it causes are not dramatic enough to match those of the orbital forcing from the Milankovitch cycles we talked about earlier. And there's a great graph in a couple of slides' time that shows you the kind of singled out effect of the solar activity in comparison to other things. So moving now towards that dramatic rise at the end of the hockey stick. And this collection of graphs is very famous and for a very good reason, because I think it just makes the argument so well for what's going on the planet. So these graphs all have this line going through them here, which is 1950. And they show a variety of socioeconomic trends and a variety of Earth system trends. So things that are nothing to do with temperature, in theory, on this side, we have population massively grows, GDP massively grows, energy use massively grows, water use, large dams, transportation, international tourism, fertilizer consumption, all of those things exponentially increase in 1950. And then what happens to the Earth systems at the same time in 1950? We see massive increases in carbon dioxide, nitrous oxide, methane, massive increase in ocean acidification, massive increase in tropical forest loss, massive increase in surface temperatures and nitrogen in coastal zones. When you put these side by side, can you really call it coincidence anymore? It's really, to me, this just says everything that needs to be said. It's a very irrefutable argument that there is a clear relationship between all of these things and all of these things. And this is why we call this era the Great Acceleration, because everything just takes off. Humanity takes off, population massively rises. We have industrial revolutions in less developed countries that pushes globally all of these things so high. And then we see these changes to the Earth as a result of it. And very dramatically, scientists have argued that this pushes us towards a new era of time, a new epoch that we dub the Anthropocene, so the era of man, basically, where what we're saying is that humans have become the overwhelming, overriding thing dictating the direction of our climate. The orbital forcing isn't powerful enough anymore. The volcanoes and the solar variability are pretty irrelevant. It's overwhelmingly driven by what humans are doing. Lots of scientists have kind of agreed to this now. There's a working group dedicated to it. And it's a very popular term in the media for obviously dramatic reasons. But because of this unprecedented rate of warming that we've been talking about over the last couple of slides, taken from all of that paleoclimatological evidence, we see that the Anthropocene is very much a real thing, at least as a concept, certainly. And officially, it has been declared by scientists. But there is a lot of debate still over the starting point of it, which we'll talk about in a minute. But just to talk about these graphs here, we have these two here, where the blue one is trying to recreate the black line, modeling only natural forces on the Earth. And you can see it does not manage to do that. The red one here tries to match the black line in a model using both natural and human factors, anthropogenic factors, and it manages to match it. So really, they cannot recreate, they cannot model, they cannot make computers recreate what is happening to the current climate without including humans on that graph. And when you look at this graph over here, the red line is our greenhouse gases, and the black dots are all of our observed temperatures, with the gray line being the kind of general trend between them with what the temperature is actually doing. And all of these lines down here are things like natural climate forces. So the orange line is the volcanoes, the dark blue line is the aerosols from volcanic eruptions and things like that. So the gray line, which combines all factors, is very clearly aligned with the greenhouse gas line and not very clearly aligned with these ones down here. Obviously, the volcanic eruptions in particular are evident in this line up here. And so no one is trying to argue that solar fluctuations and volcanic eruptions and orbital forcing don't still drive our climate, because they absolutely do. They're working in the background. But what's also driving our climate is the red line, the greenhouse gases, and that clearly is what's pushing it up in this part of the graph over here in the kind of post-1950 era. So back to the Anthropocene. How do we define that as a term? So like I say, it's kind of a term that's thrown around quite a lot in the media, but geologically speaking, as an official part of the geological timeline, as an official epoch, it needs to have something called a GSSP, or a golden spike, which is essentially a point in the rock record where all around the world you can say this is the point in the record where the Anthropocene starts. So an example of that is the end of the Cretaceous period, where the meteorite hits and all the dinosaurs die. So at that point, we see globally the sudden loss of an entire group of species, the dinosaurs, and we also see a really sharp increase in an element called iridium, which is very rare and really only comes with things like meteorites. So all around the world, you have a sudden increase in a very weird and rare element, and you have a sudden loss of a whole group of animals from the fossil record. So at that point, we can very clearly say, okay, below that point, we're in one era, and above that point, we're in a new era now. So to create something for the Anthropocene, we need something like that. We need it to be brief in time. We need it to be unique enough to be able to identify it. And it needs to happen kind of everywhere and all at once. So they say it needs to be globally synchronous, so happening all around the world and happening at the same time, so that very precise, so that each point around the globe where it's identified is linked ideally to the same year. These are used pretty much for all of our periods of geological time, going back to the Cambrian explosion, like I talked about earlier. And then prior to that, in really, really deep time, they use these GSSAs instead, which are much more loosely defined and less precise. So we've got quite a few different ideas for a start point for the Anthropocene. And I'm going to talk about a few of them in the context of their suitability for providing that golden spike, or the GSSP, that we need to identify in the rock record. So the first one that was almost the first theory actually to come about is the early Anthropocene hypothesis. This was proposed quite a long time ago now, and it was saying that we should count the Anthropocene with the beginning of kind of large-scale agriculture, because since the beginning of large-scale agriculture, that's when we've been significantly impacting our climate because of declining CO2, increasing deforestation, and things like that. So about 7,000 years ago is proposed as a start date for that. And there's also an option of 5,000 years ago from the change in methanes come about from cattle-based agriculture and rice paddies and things like that. The problem with these is that they are neither global nor synchronous, because not everywhere around the planet was developing agriculture in the same way at the same time. It was a very gradual process over thousands of years that took different civilizations to do different things with agriculture. And obviously, different civilizations did this in different ways dependent on what climate they were based in. So, the Egyptians clearly did agriculture very differently to people in Scandinavia. The rice paddy one is also different as well, because obviously rice is predominantly grown in certain parts of the world and not so much in other parts of the world. So both of those, whilst symbolically quite good ideas, are not quite as easy to pinpoint as any kind of specific point in time. The next one along is one that I quite like, especially in terms of its symbolism. So the Orbis hypothesis sets the start date for the Anthropocene in 1610. To be symbolic of globalization. So the idea behind this is that when the Europeans colonized North and South America, they went over and they colonized, and with them they brought all of the diseases that the Native Americans had absolutely no immunity to. You see a mass death of the native peoples of North and South America because of this disease, and also the general shooting that was done. And because of that, these agriculturally based civilizations suddenly stopped doing agriculture because they're dead. And as a result of that, there's huge amounts of forest regeneration because they're no longer deforesting for agriculture. So you see a big drop actually in global carbon dioxide from the regeneration of lots and lots of forest across the Americas. So that's kind of the chemical point that you look for. You look for the drop of global CO2 in the ice core. So it works as a marker. And then symbolically, it's associated with the Columbian Exchange, which is the idea that for the first time in millions of years since there was a singular continental mass in Pangaea, there is a mixing of species that have evolved completely separately from each other. The Europeans take stuff over to the Americas with them, they bring stuff back, and at this point in time you have an irreversible mixing of species across continents that were completely separate from each other, species that have never interacted before and did not co-evolve together. So it's really symbolic of the modern globalization, where boundaries are much less defined, everything is very mixed in a big global melting pot. So I quite like the idea of the Orbis hypothesis from that point of view. So fast forwarding to the Industrial Revolution, this was again quite an early idea for a start date for the Anthropocene. And again, it makes lots of sense. It's what we typically think about in the Victorians with their factories and their coal mines and their pollution. And we see big increases in sedimentary records of carbon dioxide, lots of metal-based pollution. But again, the problem is that it's very localized to Europe and North America, because obviously in the 1800s, the global north was at one point in their development, and the global south and other places were not quite there yet. They weren't at the point where they were building factories and churning out pollution. So the Industrial Revolution symbolically works for the Anthropocene, but it's not global at all. It's very Eurocentric as an idea. So another one that's a candidate is the Trinity test in 1945. So this was the first detonation of a nuclear bomb in 1945. That was the test done by the Americans for the bombs that they eventually used to bomb Nagasaki and Hiroshima. So because it was the first ever detonation of a nuclear bomb, there's this sudden global presence of radioactive material in the sediment records, which conveniently works quite well as a clear golden spike, as it were, in those sediments for the beginning of a new human era. And again, quite symbolic as a move into an era of destruction and nuclear weapons and modern warfare. And again, around that kind of 1950 point with the Great Acceleration. The Great Acceleration itself can be used in lots of ways as well. There's a particle called SCP, which is produced from burning fossil fuels. And obviously that dramatically increases around 1950 with industrialization. And importantly, it increases all over the world at that point in time, because at that point in time, the Green Revolution has happened. Lots of lesser developed nations are beginning to industrialize as well. We see fossil fuels being used much more widely on a much more global scale. So this particle is present in sediments all around the globe from around 1950. It's very distinct as well, and it's not a naturally occurring thing. It only is produced by burning fossil fuels. So 1950, another quite good candidate. The last one we're going to talk about is the peak of atomic testing in 1964. So this was where radionuclide fallout reached its peak levels from bomb testing as a result of the Cold War, the Soviet Union and America, the USA, doing lots of atomic weapons testing in their kind of arms race during the Cold War. So this sharply ended in 1963 when they signed a treaty to end the testing of nuclear weapons. So we see a big drop off in the radionuclide fallout after that point in time. So again, something that could be used to identify a start date for the Anthropocene. This one, again, has quite nice symbolism behind it, because instead of the doom and gloom symbolism of the other ones, it has almost a positive message behind it, because it's the story of destructive technology, but then the human ability to actually stop that and get on and sign treaties and stop terrible things happening. So I quite like that one from that point of view as an option for the Anthropocene. But regardless of whatever start date is picked, they're still talking about it, I think. It's irrefutable that climate change is happening. They've calculated the idea of something called planetary boundaries. So the circle in the middle with the green lines is the natural extent of different kind of Earth systems. And then where the yellow and the orange lines are is where we've exceeded those boundaries, where we've exceeded the normal boundary of that particular system. And you can see climate change has exceeded that in the yellow bit there. It's definitely an increasing risk. But quite shockingly, I think, because climate change gets so much attention in the media, obviously with things like COP26, you don't hear so much about these other ones that are clearly far, far worse than climate change. The nitrogen and phosphorus cycles are completely ruined, you can see by this bit over here. But very importantly, the integrity of our biosphere, our biodiversity, which is so intrinsically linked with the planet's climate, is in a much, much worse state. So this orange bit here symbolizes extinctions per million species years. And you can see that has far exceeded levels that we would consider normal. So the idea of a sixth mass extinction has been posed because the background levels of extinction have been so dramatically exceeded that people have suggested that this is comparable to those other catastrophic mass extinction events back hundreds of millions of years ago, like the Permian one, where 96% of life went extinct. That's the level of disaster that it's being compared to. This graph only considers vertebrates, so you can see mammals, birds, other vertebrates have drastically become extinct in the last 100 or so years. And I don't think they've been able to calculate one for invertebrates, but I imagine it would be dramatically worse than this even. So regardless of the start date of the Anthropocene, we're clearly well and truly into an era where humans are affecting not only the climate, but the biosphere and the environment and around us in all aspects as well. So we like to think that there is hope, because obviously at the moment, the ongoing talks at COP26 are trying to address some of these big issues that we've been talking about. They've been trying to work out ways that they can limit the extent of climate change, the way they can mitigate it, the way they can support nations that are disproportionately affected by it. But obviously, as I'm sure you've seen on social media, there is a lot of cynicism around whether their promises will be kept. Do we really think they're going to keep this 1.8 degree promise? Do we think that it's fair the way that, for example, Caribbean island nations are being drastically affected by climate change, but yet not really receiving the financial support they need from the global north? So COP26, as it kind of folds out, will certainly be a really interesting time for debate around climate change and where action needs to go from here. paleoclimatology, as I hope you've ascertained from this talk, has played a hugely important role in enabling us to understand the extent of climate change in our modern era, and to recognize the contribution of paleoclimate and the importance of it in the story of climate change science. There's a nice artistic exhibition that's actually being exhibited at COP26. The British Antarctic Survey donated a big slice of one of their ice cores, which in it has oxygen bubbles, real air bubbles from 1765, which they are saying is the dawn of the Industrial Revolution. This is air from before we started polluting. This is air from before we started burning fossil fuels. And they've got that there as a symbolic reminder that the extent that the Earth has changed from that point. So the remit of much of the talks that the Wildlife Trust and other people are doing around COP26 is about education more than anything, because some research has come out of international groups that saying closing the emissions gap is really dependent on closing the education gap. They've shown that the closing this gap between people's education on climate change, getting people to understand what's going on, is a better solution than 3/4 of other climate change solutions. So there is a real inequality at the moment in access to climate change education. We need to push and champion our governments putting that into things like the national curriculum more and more. People need to be learning about this science and understanding it, so that those, when they become the decision makers of the future, have a good head on their shoulders and know that they need to take it seriously. So again, to try and end on a positive note, regardless of COP26, the Wildlife Trust, other conservation organizations are pushing forward with things called nature-based solutions. COP26 has already been talking about them. Regulator chiefs has called for them in this combat climate change fight. And what we believe, as I've spoken about, is that, and Sarah Jane has spoken about, is that nature and climate change are so intrinsically linked. One affects the other, and it is beneficial to both for us to treat them often as one and the same. We can use nature to combat climate change and at the same time improve our biodiversity and create more ecosystem services, create more natural capital, create other benefits for humanity. So really, by working together, considering nature and climate as the same fight and this very intrinsically linked battle, we can have the best of both worlds. We can have nature, we can bring back our biodiversity, stop all those species extinctions, and we can also start to control our climate and create a future that is both richer in nature and richer in many other ways for the societies and economies as a result of that. So, thank you very much for listening to me waffle on. I think I've probably gone over my allotted time, but I will hand back over to Sophie now.
Ben, thank you so much. You leave me speechless every time I hear you present. You are just so knowledgeable on the subject, and you present so wonderfully. Thank you so much. Absolutely fascinating. We have got one question in. Maybe people are just taking some time to gather some thoughts, because that was such a well-stocked tour of history, really. Right, we have one question. If the history of the world is a series of cycles between icehouse and greenhouse, what makes us think what we do to reduce global warming will make a significant difference? That's a brilliant question. Thank you so much for asking that.
That is a really cool question. And to some extent, what we do as a species in the context of all of those million years makes absolutely no difference whatsoever. If we continue down the path we're on and we continue to destroy the environment and we continue to pollute the environment and increase global warming, we will eventually kill ourselves off as a species. But millions of years down the line from that, the Earth will sort itself out. Like I said at the beginning with uniformitarianism, those natural processes will continue to work. The Earth in millions of years' time will sort itself out from whatever state we leave it in at the inevitable end of humanity. But what we're trying to do in our kind of current talks and COP26 and everything is about reducing it in the kind of lifespan of humans, because that's essentially what matters to us. We're selfish creatures at the end of the day. We need to ensure the survival of our own species along with all the other species on the planet. So what we do now will make a significant difference to us and what exists currently in the next 100 years or so. Whereas in the scale of those icehouse and greenhouse phases, no difference whatsoever. What will be, and the Earth will get back to whatever state it wants to be in.
Brilliant. I hope that answered your question. Wonderful. Can I just remind you, I'm looking at 2 different screens with 7 pop-up boxes to manage this event. So please, if you could put your questions in the question and answer feature, I would be really grateful. Saves me missing a question, as your questions are really important. We do want to answer them. I have seen the question from David. So David, I will answer your question. Don't worry about that. I'm just going to finish off Christine's question. There's another couple of questions coming in. As a percentage, how many of us, I'm sorry if I'm getting this wrong, Christine, how many of us need to change and how drastically to make a difference? I hope I've summarized that correctly.
That is a very good question. I wish I knew the answer to that. I think that is probably the kind of question they're trying to answer at the moment in COP26, because really that is what we do need to answer. And when we do know that, that's what we can try and stick to. There's different kind of assumptions about what is a safe level of climate change to stay under. So it used to be that they thought we should stay under 1 degree, but it's too late for that now. Then it was 1.5 degrees, but it's too late for that now. So they think that if we manage to stay under 2 degrees, we'll be all right. But like you say, we do need to understand how many of us need to change and how drastically. And whilst individual actions make a difference and we all have our part to play, the big drastic changes need to come from governments and global corporations to make that big drastic difference, in my opinion, at least.
Yeah, absolutely with you on that one, Ben. Right, we have got another question. So are we really just trying to ensure our lives remain relatively comfortable in the short to medium term? That's a very interesting question.
Yeah, I think that was following on from what I was saying before, but yes, obviously different people are motivated by different things. For myself, and I know many of my colleagues at the Wildlife Trust, we're motivated also by our belief that the other biodiversity on the planet has a right to exist and not be impacted by our actions as well. But for many people, it is about humanity's survival and the economic and social implications that will come with climate change alongside the environmental ones.
Great answer. Right, I've got a question for Sarah Jane. I think you're probably the best person to answer this one. Excellent question. Have WWF had any input into COP26? And if so, what, please?
Well, thanks very much for that question. I mean, obviously, I can't speak in detail for WWF, but what I can say is that all of the environmental NGOs and all of those organisations are represented at COP26. I'm a member of WWF myself, and I know that they are running various campaigns at the moment that people can engage in, that people can make their voice heard through the WWF route. The wildlife trusts are doing daily updates from COP26, and I think Sophie shared the link for that in the chat earlier. So this is a big opportunity for us to bring all of our voices together as NGOs and ask for those decision makers at COP26 to take the actions that we need to take. So I hope that gives you some insight into the fact that I'm sure WWF, along with all of us as NGOs, are going to be there and are going to be asking to be taken account of.
Absolutely. Thank you very much for that question. It's definitely a sort of working in partnership. We're all in this together and all fighting very hard. We've got another question from David. David, thank you for putting your question in the question and answer function. I'm very grateful. Can you give us scenarios projecting the same indicators for the next 100 or 1,000 years for the different human emissions scenarios? And what is the correlation with global population numbers? Wow, that's a question and a half.
Yeah, I know, right?
Sorry, Ben. Brilliant question. Thank you so much.
So I would say that the best way to get an idea of that is looking at a graph rather than listening to me try and describe it. There are lots of graphs that have probably been thrown around the news recently because of COP26. And if you do a bit of Googling, you'll find some great ones. But usually people go for a couple of different scenarios. There'll be a business as usual scenario, which is worst case scenario where everyone just continues as is. And then that one can go, I think I've seen it in some models go to 4 to 8 degrees Celsius change, which would be really, really bad. And then there are often different models suggesting, okay, if everyone suddenly became fantastic today, this is what would happen, best case scenario, and then kind of some more realistic ones in the middle. So it's worth having a look at them. I'm not sure if those great acceleration graphs have been modeled in the same way, but they've certainly done them for temperature at the very least. In terms of the link with population, as far as I understand, population is still on the rise at the moment, and global populations are still quite rapidly increasing. And it's just a case of more mouths to feed, more people to house. Everyone has their own carbon footprint, particularly in this modern globalized world where we have Amazon and cars and holidays and nice things. You know, we all have those. We're all guilty of that to some extent, and that's okay. But with an increasing population, you are just, as the population needs more stuff, and that stuff comes from fossil fuels, plastics, non-renewable resources. They create more pollution through using energy in their homes, their cars, etc. They take up more land space that isn't then set aside for nature conservation or forestry or something because they need to live somewhere. So that's kind of the link with population there.
Brilliant. Thank you. Great answer. And fantastic question. Thank you very much for asking that. I've got Sarah Jane. I might come to you for this question, if you don't mind. How do we convince big businesses to put climate change ahead of profits?
I think that's a really good question. Actually, businesses, a lot of the bigger businesses, are already quite a long way down the journey of how do they think about climate change, how do they reduce their impacts, and a lot of them are now starting to talk about actually how do they become nature positive. What drives those businesses to think about those things is the risk to their bottom line ultimately. So if what we're seeing is that companies who are more directly reliant on, for example, natural resources, so companies that make paper, for example, or companies that produce beverages that rely on a reliable supply of clean water, those companies have actually been recognizing the risks to their businesses for some years. So we had a company based in Surrey that was responsible for making a range of different beers. And they have been investing in catchment management in the countries where they manufacture those beers for many years, because in order to make their product, they must have a guaranteed supply of clean water. So I think what we see is that what will drive businesses to take action more quickly is where it impacts on their supply chains, where it impacts on their profits. And so they have already been thinking about how to improve the resilience of their business. Where it's a little bit slower, and particularly, for example, in a county like Surrey, we have 65,000 SMEs in the county. And those businesses, it's much more challenging because perhaps the impacts that they experience are less direct, and they possibly have much smaller margins in terms of the profits that they're making in order to be able to implement the things that we need them to do. There are some things coming down the line which are going to force businesses to take account of both requirements to address their carbon impacts, but also importantly, as Ben was saying earlier, also to look at that nature positive side, and that is related to their financial disclosure. So the Task Force for Nature-related Financial Disclosure and for Climate-related Financial Disclosure will require statutory accounts that companies produce to actually state what their impacts are. And I think that will be a big driver towards businesses starting to move in that direction.
I think I would just add to that as well. The other big driver is policy coming down from the government. So, for example, with the Environment Bill at the moment, a great outcome of that is that there will be biodiversity net gain and there will be mandatory gain for nature as part of development. So for those businesses, like Sarah Jane said, that where the climate change doesn't really directly impact their bottom line, it needs to come down from government. It needs to encourage them through policy to get them to take action on different things, I think.
Brilliant answers. Thank you so much, Ben and Sarah Jane. We've got another couple of questions come in. Dave just said, thank you, Ben, really helpful trends and illustrations. One other question, has someone calculated a personal carbon budget per person per year, e.g. related to achieve net zero or less and less?
Interesting question. I would imagine probably someone has done that. I know there's different ways of thinking about it. Some people think about it as a carbon footprint, which is kind of your direct, the traditional way of thinking about it, like how many holidays do you go on, blah, blah, blah. But then there's also a newer concept called a carbon shadow, which is more about almost your legacy. Like, are you having children? How many children are you having? Where do you live? Where did you move to? Kind of thing, a kind of more holistic view of it. So I think it's very complicated. Because again, that kind of calculation is going to be so dramatically different for people at different wealth levels, people in different parts of the world. So probably someone's tried, but I'd imagine it's a bit tricky.
I do know that there are lots of carbon calculators out there. I know the One Planet Living campaign that WWF started quite a few years ago now had a sort of number of planets you consume, which takes into account biodiversity loss and sort of the whole sort of picture, really. So that was really useful. I think it might still be live, I'm not quite sure. Right, another question, really interesting question. If we move back into the glacial period as expected, how would this impact the human's effect, or could the human effect have stopped this cycle? Brilliant question. Thank you very much for that.
I think, like I was saying in the talk, that we kind of have stopped that cycle. I think the forecasts at the moment, the modeling that's been done, suggests that we won't be going back into the glacial period that we would expect to be going back into. So to answer your question, yes, I think we've stopped it basically. But if it did eventually happen, as it may do at some point in future, when the orbital forcing reaches a certain level, perhaps, then we'd be living in a very drastically different world. It would be much colder, lots more ice around.
Brilliant. Yes, Sarah Jane, did you want to say something about that?
Well, just making the point really in terms of the calculation. In Surrey, we did some work a few years ago, and we know that we consume as a county 3 planets worth of resources. So we're already well above the limit. In oil producing countries, that can be as high as 12 planets worth of resources. In the US, it averages about 6. So, but in most cases, we are above the sort of 1 planet that we currently occupy.
That's really quite frightening, isn't it? And I absolutely agree with you, Christine. You're excited and depressed at the same time. Absolutely with you on that. And yes, we do need to jump up and down on governments.
Yeah, I think a nice thing to finish on, because it looks like the questions have dried up, is although we've been talking about businesses and governments and we need to jump down on them and make them do things, a phrase that's really stuck with me is the idea that one person doing it perfectly isn't as good as everyone doing it imperfectly. So, like I say, we all use Amazon, we all go on holiday, we all drive cars. it doesn't matter. As long as you're doing your little bit, then collectively we do have a difference in terms of our consciousness, our awareness, and our carbon footprints as well.
Absolutely with you on that, Ben. Yes, the questions have dried up for tonight, but what an amazing questions from our audience. Thank you so much, and lots of lovely comments coming in, Ben. As always, that was completely excellent. Not my words, but I totally agree. And thank you for a brilliant evening from another person. So one last question I'll go to. Josie asked, does WWF support activists? I don't know the answer to that. Sarah Jane, I don't know if you want to answer that.
I'm sure they probably do, but again, you know, we can't sort of speak for what WWF do, but I'm sure that they have their own campaigns that they are supporting.
Absolutely. Wonderful. Well, thank you all so much for coming along this evening. It's been just an absolute pleasure to have you all with us and learn more about this fascinating subject, particularly at a time like this. And do check out the Wildlife Trust's COP26 page. You can get daily updates and hear from the chief executive. And there's some really useful videos as well if you want to educate your family or your friends about what is COP26. There's some really useful tools and information on there.